So in this session, let us discuss few more properties of homomorphism. What they are quotient ring properties. Now, what is a quotient ring? We already discussed about quotient group. Now, the quotient ring also, it is nothing but the set of all cosets. Whereas under quotient group, what we do is we have only one binary operation. Now, here we will be dealing with two binary operations. So what does the particular theorem we are going to prove state is every quotient ring of a ring is a homomorphic image of the ring. So let's have a look at this particular theorem and then how we are going to establish this proof. Right. Now let's have a look at the statement of the theorem. If U is an ideal of a ring R, then the quotient ring R by U is homomorphic image of R. Or else the same statement can be given as every quotient ring of a ring R is a homomorphic image of the ring. So what we are given? We are given that U is an ideal of the ring R. So whenever U is an ideal, we can form the quotient ring. What is that R by U? What does it consist? It consists of all cosets of the form X plus U, where X is an element of the ring R. And we know that this set forms a ring already. We have proved this one with respect to addition and multiplication of cosets. How do we define the addition? Whenever A plus U, B plus U are two elements of R by U, then A plus U plus B plus U is nothing but A plus B plus U. And A plus U into B plus U is AB plus U for all A plus U, B plus U belonging to R by U. So now let's define a homomorphism, a function first, and show that this function is a well-defined one in the step one. So let's define f from R to R by U, a function. How do we define? Whenever there is an element in R, every element is mapped to the corresponding coset A plus U for all A belonging to R. So in step one, what we defined this mapping, it is a well-defined mapping we will establish. So let us assume A and B belongs to R and say A is equal to B. Either side, let's add the same component plus U. So A plus U is B plus U. But what is A plus U? That's nothing but our f of A. And B plus U is f of B. So whenever two elements are equal, then their images are also equal, which is nothing but clearly the definition of a function. So we can say that whatever is the relation here we have defined, that definitely is a function. Now let's proceed for the next properties. What are the next properties? We need to establish that f is a homomorphism. So let's check, is f a homomorphism? So for that, let's consider two elements from R. So let A comma B belongs to R. Now let us check what is f of A plus B. What is the image of some of the elements? But what is by definition? How are we defining our f? Every element is mapped to its corresponding coset. So this element A plus B will be mapped to its corresponding coset, that is A plus B plus U. But what is coset addition? From coset addition, we are defining A plus U plus B plus U is A plus B plus U. So how can I write this A plus B plus U? I can rewrite this as A plus U plus B plus U. So the same thing we are doing over here. So this also can be written as A plus U plus B plus U. But A plus U is f of A, B plus U is f of B. So here under addition, we are establishing the homomorphism property. Now let's check under the coset multiplication. Consider f of AB. By definition, it is AB plus U. But what is AB plus U? This is nothing but A plus U into B plus U. So which is nothing but FA into FB. Hence F is a homomorphism, we can say. So now we need to check, is this an onto mapping? How do we establish onto mapping? For every belonging to this set R by U, we should show that there exists a pre-image in R. So let's consider an element from R by U. So let it be some X plus U. Let X plus U belongs to R by U. But when do you get an element in R by U? Provided there should be an element in R. So where your X is in R. So for every X belongs to R, we should have an image. What is that? F of X is X plus U. So for each X plus U belonging to R by U, we have, there exists an R such a way that F of X is X plus U. Hence, we can say that F is an onto mapping in this particular case. So F R to R by U is an onto homomorphism, and this homomorphism defined so can be called as, we call it as a canonical homomorphism. Canonical homomorphism, right? Now, let's have a look at this particular one. What is kernel of for this particular one? All the elements X belonging to R such that F of X is 0 plus U. The 0 element of R by U. So that is, what is F of X? X plus U, such that X plus U is equal to 0 plus U. This is nothing but X plus U is equal to 0 plus U. We have proved H plus H is equal to H if and only if H is an element of H. So from that property of cosets, this is nothing but, kernel is nothing but all X belongs to U, which is U. So kernel F is nothing but U itself. So what does this confirm us? This confirms us that every ideal in a ring R is the kernel of some homomorphism defined on R, we can conclude. Have a look at this particular example. Z6 consisting of 0, 1, 2, 3, 4, 5. We know that Z6 under addition mod 6 and multiplication mod 6 is a ring. And we know that U consisting of the element 0, 3 is an ideal. So 0 plus U, let us check what it gives you. Nothing but 0, 3, which is our U. 1 plus U is consisting of both two elements, 1, 4. 2 plus U is 2, 5. If we are trying to figure out what is 3 plus U, that is nothing but U. 4 plus U is 1 plus U. 5 plus U is 2 plus U. So how many? Those Z6 is consisting of 6 number of elements. Z6 by U, it consists of only 3 different cosets. 0 plus U, 1 plus U, 2 plus U here. Now let's define a function. How do we define is from Z6 to Z6 by U? F of 0 is mapped to the corresponding coset. 1 is mapped to corresponding coset. 2 is mapped to the corresponding coset. Now again, 3 is mapped to 0 plus U. 4 is mapped to 1 plus U. 5 is mapped to 2 plus U. Now let us check. How many elements are mapped to 0 plus U? Observe here 2 elements. What are they? 0, 3 here in this case. What is that 0, 3? That is nothing but your ideal here in this case. So what we can say is here your Z6 is homomorphic to Z6 by U, we can say. Or else if you take another ring, say Z3, consisting of 0, 1, 2, then we can establish an isomorphism also here in this case by defining the function as f of 0 is 0 plus u, f of 1 is 1 plus u, and f of 2 is 2 plus u here in this particular case.